So right now we've addressed completing the square using one strategy. And completing the square is, if you like, a task, not a strategy to accomplish the task. Completing the square is means just write a quadratic function as a square atom plus or omega. That's why it's called completing the square. You're trying to make choices that will result in a perfect square showing up. And we've seen why it's useful. Once you've completed the square, you can graph. Once you've completed the square, you can optimize. Once you've completed the square, you can find the x-intercepts without using the quadratic formula. And in fact, that's how you prove the quadratic formula. And so far, we have one strategy. We'll let this thing in the abstract. Set the coefficients equal to each other. Solve for A, B, and C. That's familiar from just what we did last time? Nice. So here's another strategy. It's one that'll feel a little bit more ad hoc, but well, maybe it'll be more natural in some ways. So here's the summary. Let's just perform algebra on the side that we have. So minus x squared plus 6x minus 3 until I see a perfect square show up. And in order to do that, let's just recognize what a perfect square will look like. What do you get if you FOIL out x plus b squared? Maybe even just like do it and tell me. Nice. Does anyone want another just redo of how to FOIL things? Okay, excellent. So, you get this. So, that means if I can see something that looks like x squared plus 2bx plus b squared in this, I can use that. So, what will I do? So if I can see x squared, just an x squared term plus 2 times something times x plus that same something squared on the right hand side, I can replace this by that perfect square. So let's try to do that. Here's the thing whose square I want to complete. Negative x squared plus 6x minus 3. And notice I have like something on the left hand side of the equal sign. It's just like a placeholder variable that I'm calling y. And that's handy because now I can like do something to both sides of the equation to mess around. And one difference I see between this and the form I want is this has 1 in front of the x squared. That has a negative. How would you move that negative to the other side? Well, can I make all of both sides just negative what they already have? Yeah, and that'd do the trick. Let's multiply both sides by negative 1. Negative y equals, so I need to multiply all of the right-hand side by negative 1. So x squared minus 6x plus 3. And just for convenience, I'll just get rid of this 3 entirely. Move it over to the other side. Minus y minus 3 equals x squared minus 6x. All right, so now let's focus on this 2bx term. I need the term next to the x to be something multiplied by 2. Is that something multiplied by 2 next to the x? Yeah, I guess it's 2 times negative 3 if you want to be picky. So, this side is now equal to x squared plus 2 times negative 3 times x. Oh, cool. This thing looks like a choice of b. But in the perfect square piece, I expect to see a plus b squared. Can I just add b squared to one side of this equation and call it good? No, I have to add it to both sides. But we can add it to both sides of the equation. Let's add negative 3 squared to both sides of the equation. Negative 3 squared, of course, being 9. So y minus 3 plus 9 is equal to x squared minus 2. Oh, no, I did that correctly. Well, let's see. So I would like a plus b squared to show up. And right now I have b equal to negative 3. So b squared will be negative 3 squared is positive 9. So, yeah, I think I need to add 9 to both sides. Or if you prefer, you could add 9 just to the right-hand side and then subtract 9 from the right-hand side. That would be like equivalent. Let's add 9 to both sides and just see what happens. If it's wrong, then we'll fix it. So, y minus 3 plus 9 is equal to x squared plus 2 times negative 3. So here's the thing I'm treating as my b, plus 9. And right there I see b squared. Oh, neat. Is the right-hand side of that equation now a perfect square? Well, is it x squared plus 2 times something times x? Then is it plus that same something squared? Cool. So the thing on the right-hand side is now x squared plus negative 3. X plus negative 3 quantity squared. We feel good? All right. So what do we have now? We have y minus 3 plus 9, so y plus 6. Minus 3 plus 9 is plus 6. Is equal to, oh, and I lost. Oh, was that the negative sign you were saying I lost?
Yeah.
Oh, yeah, I'm sorry, yeah. There should be a negative sign in front of the y. Yeah, absolutely. And that would have been like really annoying if I'd made it to the last step. Yeah. X minus 3 quantity squared. Now let's just get y back on its own. Does that look easy to do? Yeah. Subtract 6 to the other side. Minus y equals x minus 3 squared minus 6. Now multiply both sides by negative 1, which I would have lost if it weren't for that negative sign. Y equals negative x minus 3 quantity squared plus 6, because you multiply all of both sides by negative 1. So that process feels much more ad hoc. You have like a goal in mind. You want to see x squared plus 2bx plus b squared show up for some choice of b. And then just like do some algebra until you see that happen. How does that idea feel? One of those two strategies seem sensible? So let's do one last one. Here is one last thing to complete the square on. Y equals 2x squared plus 6x minus 5. And maybe I'll ask 2 questions back to back. Well, maybe I'll ask this. So either I can give you a chance now to just practice with completing the square and then we'll come together. Or should I talk through one more example in detail? Should I talk through it? Cool. I will talk through it. This strategy or that strategy? Strategy 1? Cool. How do people like strategy 2 instead? Okay. I think the strategy 1s have it. So, well, no, now I'm confused because I think some people, so the strategy where you FOIL out this and then set coefficients equal. How many people would rather see that one done again? Okay, none. People who would rather see the ad hoc approach done again. Okay, that's the one we will do. I'm glad I asked again. So there's the thing that I want to walk with. And remember, my goal is to get x squared plus 2bx plus b squared to show up. So, what's something on the right-hand side that you would want to change to make it look more like that? The 2 in front of the x squared. That's like 2 times too big. So what should I do to both sides to fix that? Divide by 2. Cool, let's do that. So divide both sides by 2. You will get y over 2. You know what, let's write that as 1/2 y. You can write it the way you want. 1/2 y is equal to x squared, and I have to divide everything on both sides by 2, plus 3x minus, I don't know, 5/2 or 2.5, take your pick, they're the same. Feel good so far? All right, awesome. We now see an x squared showing up. The next piece I want to see is 2 times b times x. Is 3 2 times something? Yeah, it is. 1.5, or 3/2 if you want to be like really silly. 3 is the same thing as 2 times 3 over 2. But 1.5 also works. So let's do that. So this is the same thing as 1/2 y equals x squared plus 2 times 1.5 x. Well, I put that 1.5 in red because that tells me my choice of b. Should I also move the 2.5 to the other side in this step? Let's do that. That'll require, well, minus 2.5 plus. There, now nope, it needs to be added to the other side, plus 2.5. All right. So now I know what b is. b is 1.5. So what do I need to add to both sides of this equal sign? Yeah, 1.5 squared. Maybe you could walk out that 1.5 squared is, I think, 2.25. I don't want to check that. 2.75? 2.25, okay. But I'll just write that as 1.5 squared, and it may be in the final step when I want the actual decimals. I'll use that. So let's add 1.5 squared to both sides. That'll give me 1/2 y plus 2.5 plus parentheses 1.5 squared is equal to x squared plus 2 times 1.5 x plus 1.5 squared. All right. Is the stuff on the right-hand side of that equal sign now a perfect square? Yeah. How would you rewrite the stuff on the right-hand side? The stuff on the right-hand side, is it now x squared plus 2 times b times x plus b squared? Or what b? 1.5. So that means I can rewrite this as x plus b quantity squared with b equals 1.5. Neato. Feel good right now? All right, so I guess the last step, and there is actually more space provided on the next page. It's just an awkwardness in like where the page break lined up. Let's work this out. So I'll summarize what we just did on the top of that page, just so it's still there. We started with y equals 2x squared plus 6x minus 5. And we turned that into 1/2 y plus 2.5 Is that the same as we got on the previous page? Excellent. All right. So are we basically done? Like, we're not done, but have we done all the hard stuff? Yeah. What's left to do? Yeah. Just say that louder. 4. Yeah. Get y on its own now, because we wanted the thing that y was equal to at the end. So I guess that means we have to subtract some stuff to the other side, then multiply by 2. All right. So let's do that. Maybe I'll do it in 2 steps because I am feeling like I can't do anything complicated all at once right now. X plus 1.5 squared minus 2.5 minus, and you already told me what 1.5 squared is. It's 2.25, and I think I trust you. Well, maybe I should double check how many other people also computed 1.5 squared. Get the same? Get the same? Oh, awesome. Good, then I believe it. So now I guess I need to multiply both sides by 2. Oh, and I lost the y. My goodness. Y equals 2 times x plus 1.5 squared minus, this I know how to multiply by 2, is 5 minus 4.5. Cool. We feel pretty good. Did I do anything wrong in those last couple steps? And it was a lot of steps, right? What's something we could do to double check this? Well, there are a handful of things. There's the thing I started with. Let's plug in x equals 0, because that's easy. What do you get if you plug x equals 0 into that? -5. Let's do the same thing down here and plug in x equals 0. So you'll get 0 plus 1.5 is 1.5. You square that, and you've already told me that that gives me 2.25. Multiply that by 2 is 4.5, then subtract 9. Is that minus 5 in total? All right, so I think that little checksum walks out. What's some other stuff you could do to double check this? Maybe you had access to a computer. Could you grab both sides? If they're the same, they better agree. Groovy. So, there's the second strategy. I'd call this an ad hoc strategy for completing the square. Just mess around with both sides of an equal sign until you see something that's a perfect square show up. It's more open-ended, less algorithmic, but maybe that more open-endedness is nice in some ways. So maybe I'll give one last strategy. The coefficients that I called big A, big B, and big C, do you think they're probably determined if you know what little a, little b, and little c are? Could you just always solve for them? Yeah, as long as you don't like I guess this coefficient little a better not be 0, because then there's no square to complete. But otherwise, yeah, you can. And if you did, you would get a formula. Ax squared plus bx plus c is the same as a times x plus b quantity squared, with big A equal to little a, b equal to b over 2a, and big C equal to little c minus b squared over 4a. And you know what? I haven't justified that formula in absolutely any way. If you wanted to justify the formula, well, do you think you could plug in those choices of big A, big B, and big C and expand out the right-hand side? If this is actually correct, you better get that. Instead of doing that, let's just see if that agrees with what we just found. So for this example, we had A equal to 2, B equal to 6, C equal to -5. We computed the thing that's called big A to be 2, B wound up being 1.5, and C wound up being -9.5. So let's see if this agrees with that formula. Did our big A wind up being exactly the same as little a? Nice. And it makes sense why that should be, I think. Like, that's what's going to wind up in front of the x squared. Big B is little b over 2a. And that's like slightly complicated. So let's like compute that. Little b over 2a in this example. Well, little b was 6 over 2 times 2. Is 6 divided by 2 times 2 equal to 1.5? Yeah, I think so. 6 is even, it's 2 times 3, so some 2's cancel. Yeah, that's 3 over 2. And maybe that even suggests why it's b over 2a. Trying to process of finding that 1.5, we like divided by 2 and then had to divide by 2 again because of the a. Maybe look back at the walk, see if that works out. Last time looks more complicated, but it does walk out that way. Cool. How do people feel about now just having a formula that completes the square? Should we use it to do like one example? Yeah. Let us complete the square on 1/3 x squared minus 4x plus 10. So I guess little a should be 1/3. Little b should be -4. Little c should be 10. Fair enough? All right. So what should big A be? Yeah, say it louder though. 1/3, because big A is little a. What about big B? How many people need a refresher on division by fractions? I mean, if you don't, then you have your answer already. Let's just go through it. Now here are 6. That agree? Cool. I'm going to go ahead and do it. Big B is little b over 2 times a. Oh, cool. I see division in the denominator, so I should move that to the numerator. Negative 4 times 3 over 2. Ah, that's -6. I think you lost the negative sign when you said +6. All right, what about big C? Can we compute that one too? Sure hope so. Big C is little c, 10, minus b squared, -4 squared, divided by 4 times a. And there's like a few moving parts there. Well, they're not moving. There are a few parts there, just things to compute. -4, but I square it, so that negative sign doesn't matter. And I guess we have to just do it. 10 minus... Oh, yeah, sorry. You might know that 4 times 4 is 16, but I'll leave that alone because something will cancel. I'm dividing by a third, so I should multiply by an extra 3, and then divide by 4. Now is it clear why I didn't write out 4 times 4 is 16? Yeah, and not like it would have been a disaster if I had. So it's 10 minus 4 times 3, negative 2. All right, I know big A, big B, and big C, so let's write down the conclusion. 1/3 x squared minus 4x plus 10 is equal to 1/3 x plus b, so x minus 6, quantity squared, plus c. That seem okay? Nice. So, this particular topic has gone over by slightly more than half of a full lecture. But this technique of completing the square, by whichever strategy we do it, is important because of the following. Let's use it to graph. So if you want to graph this, it wouldn't be so obvious what the graph should look like. From here, maybe it's pretty straightforward what it should look like. So you'll start with y equals x squared, and then what do you do to the graph first? Deal with the 1/3, so that will like flatten it by a factor of 3, so it'll be a flatter parabola. And then how do you shift it? Right, 6 down 2. And we see kind of a flattened parabola. And if we now wanted to get the correct, oh gosh, let's get the correct y-intercept at least. So how do you find the y-intercept? Plug in x equals 0. Does one of those two sides look easier to plug in x equals 0 than the other? Which one looks easier? The one before we completed the square. The x-intercepts at y equal, the y-intercepts at y equal to 10. Cool. That seem all right? Let's maybe read off one last thing. What's the minimum value this function takes? -2. What input produces that minimum? 6. There's something important. This lets us minimize, or maximize if it were an upside-down parabola instead. And often, you'll encounter problems where you want to make an optimal choice. And let's just see one example. Oh, there's an extra credit sales pitch. Take a look at that at your own time. So, how many people have at some point read the short story, How Much Land Does a Man Require by Leo Tolstoy? Okay. If you like, it's old enough that it's in the public domain. The Gutenberg Project maintains a library of such things in the public domain. You also have access to 2 good libraries in the city. Find it, give it a read. Here's a summary of the book. It's Russian literature. So the protagonist, Paco, whose name I think I've been told at some point is just like Cyrillic or man. Alright, so he doesn't have money or land or anything, and he's poor and sad. So at some point he makes a deal with the devil. He says to the devil, "Devil, I will give you my soul, in exchange for which you arrange that I get money and land." And the devil says, "Yeah, great, deal is made." And so he winds up acquiring money and land, becomes, I think, probably like a mean landlord at some point. And eventually comes across a group of people, a village, that gives him a very specific and interesting deal. And they say to him, "You will give us that pile of money, in exchange for which we will give you from sundown to sunup to cover as much ground as you can. And however much ground you enclose on this path you take, you will keep. But if you don't make it back to your starting point, you get nothing, and we keep your money." And he says, great, yeah, I can do that. So he gets very excited. He maybe is too ambitious, starts off at a really fast clip, covers lots of ground. Finds that the sun's setting. Well, he's back because he wants his land. And he pushes himself, the villagers cheer on his good luck on making it back all the way. And he makes it back and then immediately dies of a combination of exposure and exhaustion. With the closing line of the short story being, and so we see the amount of land that a man requires is about 6'5". I mean, it checks out. Russian Marshall. It's all sad. So there's that. There are lots of interesting lessons to take away from that. We're going to forego all of the interesting life lessons and morality stuff, and we are going to change the question of that title to not how much land does a man acquire. We are going to ask how much land can this man acquire without dying. Seem sensible? All right, so there's the setup for a problem. Let's build in some more assumptions to get a math problem out of this. And one to which the techniques we have apply. So let's add some extra rules. He has established that he can comfortably cover 40 miles walking in a single day. That's honestly probably a low ball. Most people could probably cover more than that in one day. It was all they were doing that day, and then they could sleep the day after. Right, marathoners do 26. And they do that in 2 or 3 hours, right? Then there are people who want more than that. I'm not one of them. But, whatever, there's an assumption. Let's also assume that the rule is he has to acquire his land in a rectangular shape. He's probably not going to cover enough ground that the fact that the earth isn't flat will be relevant. So we'll use just the planar model for the earth to work this problem. And let's try to ask the question. If he can cover 40 miles on foot, what's the biggest rectangle he can make? Feel okay? Anyone have an intuition for what sort of shape it should be? All right, well, let's walk it up then. So, he's going to cover a rectangle. Let's draw a picture of it. There's this rectangle. Its perimeter will be 40 miles. We want to maximize the area. And, well, let's try to build a function that models this. What are the parameters that define a rectangle? Length and height seem reasonable. I think those are the best ones to use in this case. Let's give them some variable names, and I think I even have some in mind. Let's make it an x by y rectangle. Oh, neat. So if that's an x by y rectangle, then what's the perimeter of this rectangle in terms of x and y? Two x plus 2y. I see a side of length x, a side of length y, a side of length x, and a side of length y. So the total perimeter is 2x plus 2y. Oh, cool. So that it looks like I have two free variables, x and y. Do I actually, though? Could I solve for one of them? Yeah, I think so. Which one should I solve for, x or y? Does it actually matter? I think it's so symmetric it'll be the same walk either way. Maybe just because the next line is already written one variable of x, maybe I'll solve for y. Doesn't matter which one was actually used. So, solve this for y. What do you get? I'm thinking that probably someone has solved that at this point. Negative x plus 20. Yeah. Or 20 minus x if you prefer, but that's the same. All right, so now we have x and y. Let's remember that we want to maximize the area, though. What's the area of an x by y rectangle? X times y, I think. So the area is x times y, and maybe I'll point an arrow there. This is the thing we want to maximize. But I also already know what y is. Let's use that. This is the same thing as x multiplied by negative x plus 20. Seem good enough? There's now a reasonable formula. Maybe I'll also distribute out that multiplication. Is negative x squared plus 20x. There's a thing I want to maximize. Let's just generally say what sort of shape we expect this to have at the end. What shape, if you want to graph this function, what shape would you see? Be like a parabola, opening up or opening down? Down. So the eventual graph will look like this. Oh, cool. Like, does that have a maximum value? Yeah. So it's a sensible question to ask. In order to find that maximum, let's graph it. In order to graph it, let's complete the square. So take your pick. Which of the ways to complete the square would you like to do? So I guess there's like the matchup coefficient strategy, there's the ad hoc strategy, and there's just like the formula. Should we just use the formula? Okay, cool. Let's use that. So the formula says that big A should be the same as little a, which is, in this problem, what is little a? Negative 1. Big B should be the same thing as little b over 2a, which is what in this case? Let's see, it'll be 20 divided by 2 times negative 1. I think that's negative 10. And C is b squared over 4a. All right, so that's like a big number. It's 20 times 20 divided by 4 times negative 1. Ooh, my goodness. That's an urgent ringtone. I think that works out to be 100, though. All right, so let's apply that. That means after we complete the square, this is negative, because big A is negative 1, x plus b, so that's x minus 10, quantity squared plus 100. All right, easy to graph now. Downward opening parabola, shifted how far to the right? How far up? 100. So that means I should see a point at 10, 100, and it should look like a downward opening parabola from there. Maybe it's obvious that if you pick a parameter where one of them is 0, you'll go through 0, but that doesn't actually matter though, does it? Is that picture now enough to answer the question of what's the maximum area he can capture? Yeah, let's say it. What's the maximum area that Paco can capture? $100. With what units? It's miles-ish, Is miles a unit of area? Oh, okay, you did say square. Excellent. What is the length of the rectangle that accomplishes that goal? So length of the rectangle was like the parameter we called x, right? So what was x? 10 miles. The height was the y component of the rectangle. Have we written down what y is equal to yet? Not for this particular x value, but could we figure out the y value? Yeah, y is equal to negative x plus 20 is negative 10 plus 20 is 10 miles. So it sure looks like the mathematics is saying that the ideal rectangle here is a 10 mile by 10 mile square, which will result in 100 square miles being captured. All right, cool. So on the next page, I'm going to wax a little bit more abstractly. I have 3 minutes left on the clock. So let's think about what this means in general. Whenever you see a degree 2 thing that you want to optimize, one strategy to use is completing the square, because then you can just graph it. If you complete the square on this, you'll get f of x equal to a times x plus b over 2a squared plus c minus 4, nope, b squared over 4a. So let's think about what that would mean about the graph. So let's suppose that this a were positive. Would the resulting parabola be upward opening or downward opening? Upward? If a were negative, then it would be upward opening or downward opening? Downward opening. If a is equal to 0, then it's not a parabola, it's a line. So you shouldn't be using this strategy at all. Let's also say how it's shifted. So this parameter says the horizontal shift. So it's shifted by b over 2a to the left. All right, you would go right if it's negative. And c minus b squared over 4a. Cool. So far, so good. Oh, that's enough information to graph. If a is bigger than 0, then you'll see a vortex point at b over 2a, comma, c minus b squared over 4a, and an upward opening parabola from there. If a is negative, then you'll see a downward opening parabola, and the location of this vortex will be the exact same, b over 2a, c minus b squared over 4a. And by looking at these pictures in the abstract, does that have a maximum value or a minimum value? A minimum. What input produces that minimum? b over 2a. Same question here. Maximum or minimum? What input produces that maximum? b over 2a. So, the following theorem captures all of this information. Whenever you see a quadratic function, it will have a vortex at x equal to, oh no, it's to the left, negative b over 2a. I lost a negative sign. X equals negative b over 2a. When a is bigger than 0, the vortex maximizes. When a is less than 0, it minimizes. A bigger than 0 minimizes, less than 0 maximizes. So here's now a fact. You can now forget about completing the square when it comes to optimization, and just to remember, there's the location of the vortex. That's always the input whenever you see a degree 2 polynomial that you should use to optimize. And what will we do next time? We'll just do that. Cool. All right. In the next, well, have a good weekend, everyone. Yeah. Is there a rectangle that we can see minus? Oh, did I screw up?
I don't know. The big C. Yeah.
Oh, yeah, right, it would be, right, b squared over 4a, and then there should be like a minus, oh no, yeah, there should be a negative sign, right? Yeah, but I think it still works out to be 100 with that minus sign.
Right.
So I made a mistake, but then unmade the mistake because I knew what the answer was going to be. Nice. Thank you.